Good morning. I hope you're all okay. It's 9 o'clock. It's a beautiful Monday morning. Well, it's not as beautiful as it was last week, but it's okay. The sun's there somewhere behind some of the clouds. I hope you're all doing well, and I really hope you guys are staying inside as per what the government's saying. I know they're starting to get sort of quite, well, they're going to be putting fines out and things with people, and I know that someone's been arrested over the weekend, so really important to stay inside. And it's not necessarily for your health, but it's for your parents' health, your grandparents' health, and stuff like that. So please stay safe and stay inside. Today we're going to be talking about... Oh, that's not the button I wanted to press. We're going to be talking about the chemistry of haloalkanes. And if you have a look in your textbooks, it's page 224 to 228. We're going to be talking about how we identify them, their general formula, their structure. It's a really, really important... Sorry. Got distracted there for a second. It's a really important type of chemical. Haloalkanes are used quite widely in chemical synthesis, mainly to make other things, but they do have some of their own uses in medicines and organic chemistry. We're going to be learning about a new term, which is hydrolysis, and we're going to be revisiting an old term, which is nucleophilic substitution. And I'm sure you guys can work out what that means, having done the studies before. We're going to be going through a reaction mechanism, and it's really important you remember that mechanism. It's a really simple one, but it's really important. And we're going to be talking about this primary, secondary, and tertiary term for haloalkanes. Okay, let's get on with it. If I can start winding it forward. It's one of those Monday mornings. So the first thing is these two terms. The first one, hydrolysis. It's a reaction with water or aqueous hydroxide ions that breaks a chemical compound into two compounds. It is essentially how we break up organic molecules or change them. If you are doing any form of substitution with an OH- or water, you are doing a hydrolysis. It's also used to do things like breaking esters. We're also going to be looking at nucleophilic substitution. I'm hoping you guys can tell me what a nucleophilic substitution is, but there is the definition. Please feel free to pause the video and write down any definitions you need to write down. So, what is a haloalkane? Well, it is what it says on the tin. It is an alkane with a halogen attached to it. So that means it's got, instead of all CH bonds, for example, it will have a fluorine, chlorine, bromine, or iodine. Sometimes it will have more. Now, when we're looking at fluorine, chlorine, bromine, or iodine, or the halogens, we usually denote them, if we're talking about them in general, with an X. So really important to know we denote them with an X. What's the general formula? Well, again, it's going to be very similar to the general formulas you've seen before, but we have CnH2n plus 1 X. Now, this does not work for cyclic haloalkanes, and it also doesn't work for double, things with two halogens attached to them, or it doesn't work for other bits of functionality, but that is their general formula. We have a halogen attached to an alkane. And I'm hoping you guys already know how to name these haloalkanes. But here are the steps if you're unsure. The new things are we're going to be using the prefixes fluoro, chloro, bromo, or iodo. So that's fluoro, chloro, bromo, or iodo. And do remember, if we've got more than one of these things, we have the di, tri, tetra, etc. in front of the functional group. So hopefully that's something you guys are starting to get quite good at now, the naming compounds. If not, keep practicing. It's not a problem at all. Just like in alcohols, And just like with carbocations, there are classes of haloalkanes. So we have a primary haloalkane when we have the halo group or the halogen group, and it's attached to the carbon. If we've got two hydrogens on that carbon it's attached to, it is a primary haloalkane. If we've got one hydrogen attached to the carbon that the halogen is attached to, we have a secondary haloalkane. And if we have no hydrogens attached to the carbon that the halogen's attached to, we have a tertiary haloalkane. And it's really important that you're able to identify them. Identifying them is really, really important because they do react slightly differently. Not as differently as alcohols do, but there are some differences in the rates of reaction. And you need to know what the differences are in the rate of reaction. It's quite obvious, but it's really important we keep revisiting it. But there is going to be structural isomerism with regards to haloalkanes. What does structural isomerism mean? We have the same molecular formula, so C4H9Br in this case, but we have a different structural formula, and we can see that all of these have the formula C4H9Br, and we can also see that they have different structural formulae. So this one would be 1-bromobutane, 2-bromobutane, 2-methyl-propane, and 1-bromo. Oh my goodness, there's lots of them. It's worth knowing that you have to be able to name them and identify them. So the physical properties of haloalkanes all have to do with how they're bonded. The first thing to remember, as with all these things, they are covalent bonded or covalently bonded. And between the molecules there are dipole-dipole interactions and London forces. Remember, we have halogens in there. Halogens have quite a high electronegativity compared to the rest of the molecules, so we will get some permanent dipoles within these molecules, and this changes the properties of them slightly. So the first thing to remember is, if we look at chloroethane or 1-chloropropane, we can see the general formula, or the general way of looking at it, is that the melting point and boiling point goes up as the molecule gets a little bit bigger. So chloroethane, 1-chloropropane, it gets bigger as we go up. And this makes sense, because if you think about it, we're adding another CH2 group, we're making a bigger molecule, we have more electrons in those bigger molecules, and it means that they will exert greater London forces on each other. If we look at 1-bromopropane, for example, this one here has a formula mass of 124. We have a bromine attached to it. And bromine, as you know, will have lots and lots of electrons, which means that it will undergo, it will have higher London forces. It will have more electrons that can move around, make those instantaneous and induced dipoles, and that will mean that the molecules will require that little bit more energy to unstick in order to turn into a gas, so the boiling point. Let's have a look at the London forces with regards to branching. So if we look at 1-bromobutane, 1-bromobutane is going to have a boiling point of 101 degrees centigrade. If we move that bromine over to the second carbon, we can see that the boiling point actually goes down. And the reason why the boiling point goes down is because we then have branching. So it means the molecules cannot get as close together to each other, which means that they can't exert the same London forces on each other. It gets more extreme when we move to a tertiary haloalkane, and we can see again, because we've got more branching, even more, so we're looking here at, here we go, Has he mastered the tablet yet? Definitely not. Oh, that's not too bad, actually. Apart from I've just drawn totally the wrong molecule, that's okay. We'll do it like here. So here we go. We've got something like this. And if we have 2-bromo, 2-methyl propane, it definitely cannot get anywhere near to each other as close as 2 molecules of this, for example, which is going to be 1, 2, 3, 4, 1, 2, 3, 4, and a BR. So we can see that 2 molecules of this would be able to stick closer together and exert higher London dispersion force on each other. If we have the tertiary bromo, that is going to not be able to approach the second molecule of this, which means it's going to have a lower London dispersion force. So now we look at the reactivity of these things. And if we think about it, alkanes are quite unreactive unless you burn them, which is why not much really happens with them. We can of course add chlorine or bromine using radical substitution, but we actually have quite a high reactivity of haloalkanes, and the reason for it is because of this bond here. We have the carbon, we've got the halogen, and we can see that the halogen is delta negative, so it is slightly negative, and the carbon is delta positive. They have a definite dipole between them. Remember, dipole means 2 atoms with slightly different charges, so 2 things that are opposite. So we would say that Earth is a dipole because we have a north side and a south side. And the reason why this polar bond exists is because the halogens are much more electronegative than carbon. And what they want to do is they want to start dragging the electron density, and that is not a good arrow. I'll try that again. They want to start dragging the electron density towards the halogen atom. And because of that, that means that we have this delta positive, delta negative. Because we've got this delta positive here, what will happen is if I have something that has a spare electron pair, so if I have something like, and we'll just say this is a nucleophile, we can see that the electrons want to go towards this carbon, and what will then happen is that will bond onto there. That will cause this bond here to be broken, and this is going to be your general mechanism for nucleophilic substitution in these. So firstly, have a quick look at this task. Pause the video while you do this. So complete pages 1 to 2, task 1 to 2 on page 1011 of your booklet, and have a quick read of the textbook. This will help you. The answers will be on Moodle. I did make sure the workbook and the answers were up. Someone did remind me, thank you very much, on Friday to make sure I did that. So pause this while you do this. So, welcome back. What are things you can remember about nucleophiles? So nucleophiles, they are things that have lots of electron density, and they like areas of positive charge. So they are usually electron pair donors, and they will have at least one pair or one lone pair of electrons. They don't have to have a negative charge, although lots of them do possess negative charge, and they are attracted to that delta positive, the electron deficient carbon. So some examples of it are OH-, CN-, NH3, and water. And in fact, all of these things will react with haloalkanes. Let's have a quick look at them. We can see that the OH-, we have an electron pair there, so it's able to donate that electron pair. CN- you'll learn more about in the second year, but this is a fantastic way of adding an extra carbon to your chain. NH3, good old ammonia, very, very important with haloalkanes because we can make amines, which are biologically active molecules, and a bit of common water. We can see water has its lone pair here, so it can donate that lone pair. So this is your general nucleophilic substitution mechanism. We can see we have the nucleophile. The nucleophile has a lone pair of electrons, and what happens is the lone pair of electrons are donated into that carbon. Carbon can only have a maximum of 4 bonds to it at any time. Because there's a maximum of 4 bonds going to it at any time, that means in one step the halogen has to go. So this doesn't sort of like bond to it and then it sort of goes eventually. This will happen at the same time. You will find that the nucleophile will go in just as the leaving group, or the halogen in this case, is going. We can see the nucleophile is going towards the delta positive carbon, and the delta negative halogen is the leaving group. We can see that this is the result of it. The nucleophile is now bonded to the carbon, and we end up with a halide, so halogen minus iron, so halide ion. Really important that you know this mechanism. We'll see a couple of examples of it, but just remember it is a one-step mechanism. It all happens at the same time. You don't. I know when you do the electrophilic addition, we end up with a carbocation hanging around. You don't get that in this case. It is a one-step process. Okay. So if I have something like potassium or sodium hydroxide and I reflux it with a haloalkane, usually you add a little bit of alcohol to it as well, just to make sure the sodium hydroxide or potassium hydroxide is able to be in contact with the haloalkane. Haloalkanes don't usually mix with water. Haloalkanes are usually more dense than water, so sit at the bottom of the reaction vessel. So you sometimes need a bit of ethanol just to move it along. And what will happen is, if you do a nucleophilic substitution with, for example, this is a bromoethane, you will see that you end up making ethanol and sodium bromide. Works really easily. It's quite an effective reaction. And what's happening is the OH minus, and remember the curly arrow goes from the pair of electrons, so I would go a little bit closer than that, goes in, and at the same time the CBr bond is broken. So this is a one-step process. Really important to remember it's a one-step process. And the result is that we make some ethanol in this case, and we let out a bromide ion. Because it's reacting with an OH minus ion, it's breaking the molecule up, this is known as hydrolysis. So this is your animated mechanism. Oh, it's beautiful. I'm sure I should do some sort of a commentary here. And the nucleophiles attacking the haloalkane. Haloalkane's not liking it. Haloalkane's breaking up, and we end up getting a halide ion with the alcohol. That was the most exciting. I don't know where they get these animated mechanisms from. They are amazing. I have no idea how I'd make one. I might have to have a go. So we need to talk about the reaction rate, and the exam board says that you need to know about the reaction rate. If we know the CX bond, so when we're talking about CX, we're talking about it's carbon, fluorine, chlorine, bromine, or iodine. So X is any of those halogens. What will happen is they will break at different rates. So a carbon-chlorine bond will break at a totally different rate to a carbon-bromine bond. And this tells us about the strength of the carbon-halogen bond. We can see, as we expect, carbon-fluorine, because carbon-fluorine fluorines want to bond to anything, that is a really strong bond, and it's difficult to break. We can see the carbon-iodine bond is actually the weakest bond. It's about half the strength of the carbon-chlorine bond, and it's very easy to break. So what's this going to tell us about the reaction rate of the carbon-halogen bond breaking? Which one's going to be quicker? Is the carbon iodine or the carbon fluorine bond going to break more readily and at higher rates? What I'm hoping you're saying is actually the carbon iodine bond would break more readily. It's the easiest one to break. And you'd be right if you said that, and that is because if you think about it, the activation energy for the carbon iodine bond breaking is going to be lower. So if we were looking at a Boltzmann distribution, oh, that's a really bad one. Oh, well, at least it disappeared. At least I don't have to save the embarrassment there. There we are. If this is the carbon fluorine activation energy, this, for example, would be the carbon iodine activation energy. So we can see that actually more particles would have the correct energy to break that, so therefore the rate of reaction would be slower. So the other thing to remember is, although carbon fluorine would be the more polar molecule, so it would actually attract your nucleophile more, it's also the hardest to break. So if we can have a look at this, the bond strength is lower going down the halogens, and therefore the rate increases going down the halogens. If we have a look at whether they're primary, secondary, or tertiary, what we find is that the primary is hardest to break and the tertiary is easiest to break, with the secondary being in the middle. And we also have how readily something will hydrolyze, and this is going to be due to the group that's going on there. So water is less than ammonia, is less than OH minus, is less than the cyanide group. The top two are the ones which are most important, and in fact, if you were to remember just one of them, the top one is the most important there. So please make sure you remember this. Oh, that was my attempt at a star. And there I was thinking I'd got this tablet thing down. Oh goodness, that's just a mess now. We'll ignore that and move over to the next slide. Something that comes up quite often in exam questions is how you would work out what this rate of hydrolysis is. And the way that you would do it is by looking for the presence of the halide ion. So we put some AgNO3 or some silver nitrate into the solution. We add the thing that's going to hydrolyze the ions, and then we see what happens. So if I have bromoethane and I put some water in there and I put some silver nitrate and things in there, what is going to be the colour of the precipitate that forms when I have bromide ions present? What I'm hoping you're saying is that they're cream. If I have chlorine, it should be a white precipitate. If I have bromine, it should be a cream precipitate. And if I have iodine, it would be a yellow precipitate. And I've just caught myself saying something silly because it's not chlorine, bromine, iodine. It's chloride, bromide, and iodide. Have a quick read of this here, because what I would say is that this is quite an important concept of how you'd make it a fair test, etc., because this does sometimes form the basis of exam questions. So have a quick read of how you would make this a fair test. So this is what the experiment would look like. So this is with a primary haloalkane, a secondary haloalkane, and a tertiary haloalkane. and we can see that they are all bromo, which means that actually they should all be going that colour eventually. So we can see that the rate of reaction is highest when we have the tertiary haloalkane. Right, these are your tasks, so please have a look through, read the pages described, have a quick look through the booklet, and complete those bits of work. I shall stop now and I shall get this video sent off so that you guys are ready to do those jobs. Please pause this, or I will also put the task menu down on the comments for the film. Thank you. Have a good day.